Namaste and welcome back to this FreeRTOS series which we have created using ESP32 DevKit and the ESP-IDF platform. So up until now, what we have discussed is task APIs, delay, that is delay and delay until APIs. Then in the last video, we discussed about idle and tick hook. In this video, we will see what priority is, specifically task priority, and we will set them directly in the task create APIs, as well as set them using the dynamic APIs at runtime. In the end, we will also use another API so as to have a look at all the tasks managed by the kernel, along with the respective priority, the core ID they are running on, as well as their state. So hang on tight and stay tuned till the end. Alright, so I am in VS Code and this is how our code looked. So I just remove the idle as well as tick hook related part so as to have a much cleaner code with me. I'll also remove this print statements. I will also make sure to check out menu config, and within that just have a look whether the configuration of idle hook as well as tick hook are disabled. So I have already disabled them. If you have them enabled, make sure to disable them. Alright, so right now both of my tasks are at priority 1. Let me just upload this to my board and show you how it is getting printed in the monitor window. Alright, so we have the window with us opened. Let me just hit pause and zoom. We will see what happens after we return from the app main program. Alright, so first print statement is from task A. Then it is from task B. Again from task B. Let's understand what is happening here, since both of them has priority 1, right? So once app main has been exited, what happens is that first task A is created and like task A is printed, then task B prints the statement. But since we are using vTask delay until, which takes care of the periodic execution of a task, that's why task B is printed again after an interval of 1000 milliseconds. Then task A, and then the sequence is followed. All right. Let me just update the priority of task B to 2. And we will build and just observe what happens in the monitor window. All right, I have the print statements with me. Let me just hit pause and zoom. All right, once again, when we return from app main, we'll see the print statements. But this time, the first statement is from task B and not A, as observed in last time. So why is this change? This time the change is because once we exit from app main, task B is created at a higher priority, and hence it prints its statement first. After that, task A is created and its print statement. Now, since we have delay until as well as higher priority for task B, the sequence is same from here onwards. All right. So this is how you set up manual task priority by directly entering manual numbers in the task create APIs. Now, we will be using dynamic APIs, which are, let me just go on, search task priority. We'll be using task priority get as well as task priority set, these two APIs. For this, we need task handlers. Now, what is task handler? Basically, it is something that points to a given task. So I have created two task handle here. One is dynamic and static. I mean, both of them represent different tasks. This is for task A, since it uses dynamic memory allocation. This is for task B, since it uses static memory allocation. That was the idea. All right. So now we have to see in uxTaskCreate where task handle is called. Search for it. Alright, in uxTaskCreate, task handle is the last argument. But for uxTaskCreateStatic, we get task handle in the return state. So let me just quit it there. Now we will make use of these two APIs. You pass null as a task handle when you are talking about the task itself in which this function is called. Alright. You can also pass the handle of this task. That's no problem in that. Now to get task B priority, I'll just be passing the handle of task B. For task priority set API, we need to pass the task handle as well as the new priority. Let me just build this and flash it, then monitor it, and then I'll explain what it is actually doing. Let me change the priority of task A to 2 as well. Then run it again. Alright, so making some minor adjustments and then eventually flashing it, I got what I needed in my output. So basically the idea is that we want task A to remain at priority 2 while I want task B to swing between priority 3 and 1. So let me just show you. After we exit app main, task B is called, and then we print the statement priority B and priority A, priority 3 and 2 respectively. Then we call task A, and this time the priority of A is 2, but the priority of task B is 1 because we have subtracted 2 from it. Then again, we increment task priority A by 1 and provide it to task B. So that gives us 3. And then again 1 and 3 and 1. So basically we kind of juggle between the two priorities, 3 and 1. We once make task B at a higher priority than A, and then once make it at a lower priority than A. So this is use of dynamic APIs. Let me just show you another API that is useful to print the list of tasks which is managed by a kernel. So let me just show you the task that is task. So this is that API, TaskGetSystemState, and we will make use of this API. I will just create another task, task C, which would be at a much higher priority than the available two tasks. So this particular API has task status underscore T pointer. Now task status is a structure which has all the details regarding a certain task, that is task name, current state, priority, and then eventually core ID. And we will basically make use of this. So we will make use of this API to get the total number of tasks that the kernel would be managing at a given time. So what we have done here is that we have taken the total number of tasks and then we have dynamically allocated memory for that number of tasks and basically we will be giving each of these tasks their own task status underscore t structure based memory, and that is what we are allocating. So now just pass the values. This will basically return us the total number of tasks. You can also see an example. Now we will check each of these arrays which are populated with the respective task values, and let us just print them out. So task status, one thing is PC task name. So since this is a pointer to a structure, we will be using this particular symbol. Lastly, state. Now state is an enum, so it will give us a integer value. I'll just create an array with the naming sequence. And I will execute this task C at a rate of 1 second. But since this task get system uses a bit of time of the scheduler, that's why what I will do, I'll use something known as a semaphore, which is kind of like a flag. And don't worry, we will discuss semaphore in the upcoming videos. It's just I would be using them right now. And you can consider them as a signal based flag, which basically tells you to execute something. So I'll be creating two semaphore handles. Alright, so I'm done with the code part. Now why am I using this semaphore? Because this is a high priority task, and what I want is that I want to execute this task after each of this task get executed separately. Let's say task C is first executed, then I want task A to be executed, again task C, again task B, again task C, and this whole sequence should be repeated. Why I am doing this? So that I know the status of task A and task B after every function that has been ran. So after running task A, I want to know what is the status of A and B. After running task B, I want to know the status of A and B. So this semaphore are something like a flag signal condition. Let me just go build it, flash it, and then go to monitor window. Okay, I missed the library. Wait a second, wait a second. Let me just exit this and tell you one more important thing, that is the menu. So in component config, FreeRTOS, and then kernel, you got to make sure that you have enabled config use trace facility, and then config use stats formatting functions, and then enable display of X core ID in vTask list. All of these three should be enabled. Otherwise, there would be some issues. All right, let me now go to flashing point. All right, let us see what is happening. Once app main is exited, we see all of the tasks which are managed by the kernel. In this instance, that is task C, A, B, and then we have idle 0, idle 1 on core 1 and 0. We have our main task on core 0. Then we have IPC, ESP timer. So there is one interesting thing here. That is, all of the other tasks have a specific core, but not task A, B, and C. They have some random gibberish values in their core. Why is that? Because the reason is they don't have any affinity to a particular core. and ESP32 kind of can juggle them between cores if needed. So what happens is that first priority of task A and B is both set to 2. Then afterwards B is set to 3, A is set to 2. After that A is set to 2 and B is set to 1. So you can see it, we have verified it with our priority statements that we mentioned earlier in the tasks. All right, let me make use of that API that we discussed in the first video or second video, that was pinned to core, and see if that makes any changes. So we have pinned to core, and it's similar to uxTaskCreate, but in the end we have to mention our core ID. So I will just now let me build and run it. So now you can see that task A has value core 1, right? And not some gibberish value as compared to B and C, because it has been pinned to a particular core. All right, so that is it. I will wrap this video around here. We discussed about how we can change the priorities directly in the task APIs. We used dynamic APIs like TaskPrioritySet, TaskPriorityGet, and eventually we made use of TaskGetSystemState API and had the list of all the tasks which are managed by the kernel along with their respective properties. And in the end, we also pinned our task to a particular core to show you the difference that it makes. Hope you enjoyed this video. If you did, do not forget to like, share, and subscribe the channel. It would mean a lot. This is Avinashee Tech, signing off.